I would like to create a rectangular orchid garden that abuts my house so that the house itself forms the northern boundary. The fencing for the southern boundary costs $4 per foot, and the fencing for the east and west sides costs $2 per foot. If I have a budget of $80 for the project, what are the dimensions of the garden with the largest area I can enclose? The problem involves some kind of geometry, rectangular, and so it's always a good idea to draw a diagram. We are building a rectangular garden, so we draw a generic rectangle. We then build the fence for this garden, but we do not need to do so for the northern side because the house itself forms the northern boundary. The fencing for the southern boundary costs $4 per foot. That is the cut. And the fencing for the east and the west side costs $2 per foot. And that is the cost of the material. If I have a budget of $80 for the project, this will be our constraint. What dimensions? So we're looking for the length and the width. Those are the unknowns. We need to find these in a way that they will maximize the area, the largest area. Our objective will be the area. The area of the rectangle is the length times the width. The constraint is money here, but how do we come up with this $80? $80 is the cost to buy the material for fencing. We label the width as W for this garden and the length as L. Then the cost to fence the length is 4L. The cost to fence the left side is 2W, and the cost to fence the right hand side is 2W, where L is the length in feet and width W also in feet. For example, if we were to use 1 foot for the width, then the cost will be 2 times 1. If we use 5 feet for the width, then the cost will be 2 times 5, and so on. And this will be the cost. And this is the constraint. And so we are optimizing the area subject to this constraint. The cost that we can incur is up to $80. That is the budget. It can be lower than $80, but it cannot be more than $80. Simplifying the cost equation, we have 4L plus 4W equals 80, or should we use less than or equals? L plus W is therefore less than or equal to 20 because we divided by 4 both sides of the equation. And if we pretend that this is an equation for the moment, then we can isolate L to get L equal 20 minus W. Then the area is now length times the width, but the length is 20 minus W and the width is W. This is 20W minus W squared, and this is our area function, the objective function in terms of W. Note that W cannot be negative, and we can also determine the domain of W by looking at the constraint here. W cannot be more than 20 because if W is more than 20, then the length is negative, which is impossible. We then take the derivative with respect to W. The derivative of 20W is 20, and the derivative of W squared is 2W, and then we set equal to 0. Negative 2W equals negative 20, and so W equals 10. This is the width. And the length is 20 minus W, but W is 10. 20 minus 10 is 10. This means in order to obtain the largest area, we would need to build a rectangular garden such that the length is 10 feet long and the width is also 10 feet long. Now, how do we know that this combination will give us the largest area? We can use the first derivative test. The critical number that we found is w equal 10. If we plug in a number between 0 to 10, such as w equals 1, into the derivative, then we see that this is 20 minus 2, which is positive. If we plug in any number between 10 and less than 20, such as w equals 11, into the derivative, we see that 20 minus 2 times 11, which is negative. What this sign chart is telling us is that the area is increasing up to 10 and then decreasing. This means the area is maximized when w equals 10.